Thank you.
Good morning, everyone. Welcoming you all on the second day of this workshop. For this, I want to request Dr. Vikrodhar sir, please join me.
Okay, thank you. It a little bit. Can we make it straight? Okay, I think that should be good. Yeah. All right. Good morning, everyone. So, how is everyone doing today? Good? How was yesterday? It was too much information? Okay. So, today, I think you are going to have lecture in the morning session, and in the afternoon session, I think you have a very exciting field trip, right, to a wastewater treatment plant. Today, actually, yesterday we learned about some more on fundamental side, like how environmental bioprocesses works. Then we learned about half reaction, including cell synthesis, and then we learned about different characteristics of wastewater, right? So, like talking about BOD, COD, VSS. So, in today's class, actually, I want to cover 4 topics. Okay, so yesterday we learned about different stages of wastewater treatment, but in the introduction or background part, we are going to learn little bit in more detail about different bioreactor systems that we can use for wastewater treatment. Okay, so we talked a lot about activated sludge process, but there could be other systems like that you might face in the future. So, I just wanted to actually introduce them to you, like different option that we have for wastewater treatment, and then we are going to actually jump into one very important topic. Okay, so which is microbial kinetics and their role in wastewater treatment, because end of the day, we learned that why microbes they treat our wastewater or remove the contaminants from our wastewater, because they wanna grow, they want to generate energy from the process, right? So, so microbial growth kinetics, it's a very important aspect in designing biological wastewater treatment processes. Okay, so and if we know the kinetics, so what do you mean by kinetics? Any thought? Yeah, so it's rate, like how fast or how quickly microbes can actually remove the contaminants from your wastewater, right? So if we understand the kinetics, because we want to make the process faster, right? Faster process means a smaller system. Okay, so that means it is going to be more cost effective, like in terms of capital cost, and faster process your operating cost going to be lower as well, right? So that's why it's important to learn the microbial kinetics. Okay, and then after learning microbial kinetics, we are also going to learn about what are the important parameters in the process. Okay, and then we are going to actually learn about application of design equation. So if we know the kinetics, if we know the actually different process parameter in design equation, basically they combine them. Okay, so we kind of come up with some mathematical equation that we can actually use as a design tool for the process. Okay, and that's the main idea. So if we have some equation, because either you are scientist or engineer, okay, So we will have equation. So if we have some equation, we can look into that equation. We have some kinetic parameter, okay, and if we have some design parameter there, right, so we can try to actually change the design parameter and we can see how the system behaves, right. So that's the main idea. And then finally, actually I was not planning to put that topic, but after yesterday's discussion I was actually encouraged to put the fourth topic, which is biological nutrient removal. So we are going to learn, like, you know, initial plan was to focus more on carbonaceous BOD removal, but now I thought, okay, it would be better to actually kind of touch a little bit on biological nutrient removal process as well, because it's a very important topic. Okay, so let's move on. Start with the topic number 1. So we learned that actually microbes, they can be used to actually remove contaminants. Okay, and most of the time in wastewater treatment operation, the primary goals are to remove BOD, right, and suspended solid, right, because most of the regulatory guideline in most of the countries, they have the, you know, like the limit for BOD and suspended solid if you want to actually dump your treated wastewater into surface water, right. So most of the time this is the regulatory guideline, and some cases nutrients actually removal may be an objective. Okay, so if you are actually dumping your wastewater in surface water, and if your you know, treated wastewater contain like nitrogen and phosphorus, then it can actually kind of create some problem, right. You can have eutrophication, like, you know, summer algae bloom, and that can actually deplete the dissolved oxygen in the surface water bodies. So that means it can interfere with the growth of aquatic microorganisms or different types of organisms plus plants. So basically damage the aquatic ecosystem. So we cannot overlook that. Nutrient removal can also be an objective. So and we learned that actually microbes, they need electron acceptor, right, and one of the major electron acceptor is oxygen, okay, that is actually provided in the system in dissolved oxygen, right. So we learned from the the BOD measurement method. So depending on the oxygen level, okay, so we can have 3 types of processes. Excuse me. So we can have aerobic process, we can have anaerobic process, and we can have also another process called anoxic process. So what is aerobic process? So aerobic process, where actually we utilize aerobic microorganisms. So aerobic microorganisms, basically they degrade the organic compounds in your wastewater. Okay, so they oxidize the organic compound and then they actually convert them into carbon dioxide and water, right. So if we write a simple reaction, organic matter plus oxygen, and then you have product water, carbon dioxide, and there could be other end product, like, you know, more biomass formation, right. And dissolved oxygen level in aerobic process is maintained typically maintained more than 1.5 to 2 milligram per liter. Okay, and a very common example for aerobic process is aerobic activated sludge process, which is kind of like very typical process. We are mentioning this process again and again, and we are going to actually like mention that many times in today's lecture as well. So the second process is anaerobic process. So anaerobic process is basically we utilize the microbes that actually do not need any oxygen. Okay, so for their metabolism you don't need any electron acceptor. Okay, you don't need to provide any electron acceptor there. Okay, so basically they can use organic molecule as electron acceptor, and most of those anaerobic process, organic matter or any types of organic contaminants, they can be converted into carbon dioxide plus methane. Okay, so carbon dioxide plus methane, and if we write a reaction, so basically organic matter, they are going to be degraded by anaerobic microbes, and you are going to have methane, carbon dioxide, and there could be other end product. Yes.
For anaerobic digestion.
Mm-hmm. So it's a kind of, you don't provide that from outside, it's more like fermentation process. Okay, So basically larger organic molecule going to break down into smaller organic molecule and gas.
Some smaller acids.
Yeah, it could be volatile fatty acid, it could be some gas, hydrogen gas, okay. Sometimes hydrogen gas can be produced, and the final process is actually methanogenesis. We are going to actually learn in detail tomorrow. Tomorrow we have we are going to have lecture on anaerobic digestion process, but yeah, there could be a lot of other, you know, like soluble metabolite as well. Okay. So DO concentration typically for anaerobic process, those microbes are very sensitive, okay, and you have to maintain very low DO concentration, less than like, you know, 0.1 milligram per liter. So complete anaerobic condition without any oxygen. And a very typical example is, as I was telling, anaerobic digestion. We are going to actually learn in more detail tomorrow on anaerobic digestion process. And the third process, which is kind of in between, okay. So we call this process anoxic process. So anoxic process, okay. So dissolved oxygen level you still need low, okay, but system actually utilize dissolved oxygen, okay. Not dissolved oxygen, but system utilize, like, you know, chemically bound oxygen, okay. It can be in the form of nitrate, or yesterday we learned about, like, you know, when we are talking about giving the example of acid mine drainage, sulfate reducing bacteria, right, sulfate. So you can have anoxic process, and a very common example for anoxic process in wastewater treatment is denitrification process, okay. So nitrogen removal in biological treatment process, first step is nitrification. You convert ammonium to nitrate, okay, in presence of oxygen, and the second step is nitrification. You convert nitrate to nitrogen gas, okay, and that process is anoxic because we use nitrate as electron acceptor, right. So there is some chemically bound oxygen in there, and dissolved oxygen level typically still less than 0.2 milligram per liter. So regardless of any kind of process you use, either aerobic, anaerobic, or anoxic process, okay. So what we need? We need a bioreactor, right. So we need a bioreactor where we are going to have microbes, okay, and wastewater going to actually flow through the process, okay, or bioreactor where microbes going to contact with the organic contaminants, okay, in your wastewater, right, and then they are going to actually degrade, right. So depending on, so microbes in bioreactor, they can be either in suspended form or they can be attached in some media, okay, they can be immobilized in some media. So when microbes, they are actually in suspension in the bioreactor, we call this process suspended growth process, okay, because microbes, actually this is actually a diagram, simple diagram showing in a bioreactor you have wastewater in, wastewater out, and you have microbes in suspension, okay, and this is kind of completely mixed. So those microbes, when wastewater is actually entering the system, you have the contact with organics, and microbes going to degrade the organics. So microbes, they are retained in suspension, but one of the major challenge of this kind of system, okay, is wash out of microbes, because if you want to treat your wastewater, you have to make sure that microbes, they kind of remain in the system, right. But if they wash out from the system, you don't have any treatment, right, because then so that's why we want to make sure that we provide enough time, okay, we provide enough time for actually microbes, they can actually grow within the system, right. But the problem is, if you want to provide enough time, so that means we have to operate those bioreactor at very longer residence time. Then what happen? So yes, we can do that, but then we need a bigger system, right. So we need a bigger system that going to actually increase our cost, right. So that's why actually when we have this kind of suspended growth process, one of the common approach to actually kind of retain the biomass within the system, okay, is basically we can recycle the biomass, okay, or we can actually put a membrane. So I'll also like draw it on the board, like, you know, how it's going to look like. So for example, activated sludge process, what we do, we have an aeration tank where we provide oxygen, we have microbes, okay, it's completely mixed. So what we do, that aeration tank is followed by a settling tank where actually we settle the biomass, okay, and then effluent gonna actually leave the system, treated wastewater, and a portion of that settled biomass we recycle it back in this reactor to maintain a certain level of microbes, okay, and then a part of it we kind of take it out from the system, okay. So so you can either use a settling tank, another option could be a membrane, okay. So instead of a settling tank, what I can do, another thing I can actually put here could be a membrane or filter. So basically that's going to actually remain all the solid, okay, and you are going to have very clean water, okay, outside, okay, here from here as an effluent without any suspended solid. And we can do the same, a portion of sludge we can recycle back and a portion we can actually take them out from the system, okay. So this is actually yes, but microbes, they are still going to be in suspension, okay. So yes. What happened?
Honeybees, I guess.
Oh. So should I continue? Okay. So yeah, welcome back everyone after unexpected break. So we talked about suspended growth process. Okay. So where microbes, they are going to be in suspension, but one of the major challenge with this kind of system is biomass washout. So and the typical approach that is actually used to retain the biomass inside the suspended growth process is either we can use recycling of biomass. Okay. So we can have the bioreactor can be followed by some settling tank where we can settle biomass and recycle them back in the system. Another approach could be membrane separation. So we can actually retain all the solid, okay, and we can get a clean effluent without any suspended solid, okay, and then we can recycle some of the biomass, okay. But you cannot just recycle the 100% of the biomass, then actually it's a system gonna be actually very overloaded, right. So we have to actually continuously discharge a portion of the biomass to make sure that we can maintain certain concentration inside the reactor. So another process is to actually avoid the washout of biomass. Another approach that we can use is attached growth process, okay. So attached growth process can allow us to overcome the washout that we often face with suspended growth process. So how that process work? Actually, instead of microbes, we instead of keeping them in suspension, we can have different types of inert media, okay. It could be it could be plastic media, it could be some other biomaterial, okay, where we can actually attach the biomass, okay. So more like a biofilm system. Microbes, they are going to form biofilm on those inert media, okay, and then when wastewater, we can still have wastewater kind of flow through the system where actually microbes and your organic contaminants, they are going to have interaction and they are going to be removed in the process, okay. But because they are actually more attached to the media, they can be easily retained in the system, okay.
I have a question.
Yes.
That membrane, because I haven't seen anywhere this. So is it like MBR?
MBR, yes, you can say membrane, sometimes actually they also instead of putting it outside, you can also put it inside. There are many different configuration of MBR these days.
So ultimately sludge will be settled in the bottom, right? Even the install membrane.
So here we showed that okay, it's a separate unit. Sludge gonna be sludge gonna be actually retained in the system, okay. But yes, you can instead of outside, you can put the membrane unit inside, okay. But you still, in that case, you have to directly waste some sludge from the reactor, okay. Yes, there are many different configuration of MBR, but MBR is not very typical because MBR, maintenance and capital investment for membrane is really high. So sometimes it's kind of like a deal breaker for municipalities because they wanna actually reduce the operating cost, right. So typically membrane is not widely used, okay. But maybe for some industrial wastewater, maybe yes, that might be an option, okay. So yeah, industry, when they are actually limited by footprint, okay, and they are okay with spending little bit more money, but quick treatment process, okay.
Still, I also feel it's not very successful.
Well, I don't want to actually criticize any technology here, but yes, there are some challenges. Yeah, so that's why it's not widely used, right? So, and there are challenges everywhere, and that's why industries or they need people like us, right? People like you. So you can activated sludge process. It was developed in I think more than 100 years ago, but still we are doing a lot of research how we can actually make this process more efficient, right? So how we can actually incorporate multiple process in one bioreactor, right? So there are a lot of research. So there is not a standalone solution to anything. So so now we learned that actually the process could be either anaerobic, aerobic, or anoxic. Process can be suspended or attached growth process, right? So So we can have different types of reactor system. So aerobic suspended growth process. So one of the common example is activated sludge process. Another process we can have typically used for small scale wastewater treatment plant, okay, a process called SBR or sequencing batch reactor, okay. There could be a process which is aerobic but attached growth process. So for aerobic there could be both attached and suspended growth process, okay. And the common example for suspended growth is activated sludge process, and common example for aerobic attached growth treatment process is trickling filter and rotating biological contractor. Actually, I am going to provide some more detail on each process, okay. So, and for anaerobic, we can have one of the common design that is used in industry is CSTR. So actually this is a completely mixed system, okay. So completely mixed system is the concentration of your biomass or contaminants inside the reactor gonna be same in the effluent, right. So when you have a complete, so CSTR is a very common design or conventional design. So this is actually also a CSTR, like completely mixed, right. This is also a CSTR. For anaerobic process, there could be anaerobic filter, okay. So you could have a packed media, okay, where actually wastewater can flow through the media, and there is another process. But filter type of system, one of the common challenge with running filter type of system is your wastewater should be actually free from any suspended solid. If you have any suspended solid, so the filter media can be clogged, right. So that's why this is a common challenge with running any kind of biofilter process. So sometimes that's why to avoid clogging, another process is used where actually instead of, if you have a packed bed of media, you can actually like have those particles, they can be fluidized within the system, okay. So there is no clogging. So which is called anaerobic fluidized bed reactor or bioreactor, FBR. So aerobic suspended growth process, we are gonna discuss this again and again. We have a CSTR reactor in aeration tank where actually it's completely mixed, and then that can be followed by a secondary clarifier, okay, where actually like you settle the biomass, recycle a portion back to the aeration tank and waste a part of it to make sure that you can maintain a certain biomass concentration, and then finally you can have supernatant, can be clean water, okay, without any suspended solid. But we are going to learn in more detail about activated sludge process. Another process I was talking about, aerobic suspended growth process, is sequencing batch reactor or SBR, okay. So in activated sludge process we have multiple tanks, right. So one is bioreactor and one is settling tank. But when you have a small scale wastewater treatment plant, they may not have enough actually funding to actually build multiple tanks, right. So instead of having multiple tanks, they can have the whole process in one single tank, okay, one single tank, but in batch process, okay, in batch process. And that can also be actually useful for industrial wastewater. Let's say in some industrial process they are actually running in batch, okay. So for example, like some brewery industry, it could be run in batch. So wastewater that you generate, okay, its wastewater flow also going to be in kind of not going to be in continuous. So what we can do, like they can actually treat their wastewater in a batch process using this kind of system. So for SBR, this is kind of like a modified form of activated sludge process. So we can have a single tank, okay, where we put our wastewater, okay, and then we run the aeration, we supply oxygen and provide them certain time. So microbes, they can degrade the organics, okay. So after a certain period of time, when we kind of feel that okay, the treatment process is done, okay, you kind of stop the mixing. So when you stop the mixing, you have the solid gonna settle, okay. So and your clean water like gonna be at the top, right, supernatant. So we can take the effluent out and we can take a portion of the settled sludge out from the system, and then we can actually do this process again. We can have another batch of wastewater, we can fill it again and provide aeration, then after a certain period of time you can stop the process, take the effluent and sludge out and start it again. So SBR, it's unlike conventional activated sludge process, okay, we use a single tank. So activated sludge process we need multiple tanks, but here everything is done in one single tank, which is kind of convenient, like small footprint. But again, maybe large scale facility, maybe it's not going to be a feasible option. So another process that can be used for aerobic but attached growth process, okay. One of the common process that is used is trickling filter. So trickling filter is, you have actually a bed of media, okay. That media could be different types of material. It could be rock, it could be waste coal, gravel, or any kind of like specially manufactured media like plastic media, okay. So you have a big bed of media, okay, and you are going to actually use a rotating sprinkler, okay, that is actually going to distribute your wastewater, okay, from the top, okay, and when that actually wastewater going to trickle through the filter bed, okay. So how it's going to look like? So you have those media. So wastewater going to actually trickle through the media bed. Where is another? There should be another pen, but oh yeah, okay, here. Right. So you have actually microbes here, okay. And when actually wastewater going to actually flow from top to the bottom, you are going to have microbes going to have interaction with the organics, and then it's going to treat, okay, the wastewater, okay. So typically this kind of process can be feasible for small scale wastewater treatment plant for small communities, okay. But one of the major challenge with this kind of system is you have to have primary treatment, okay. So you have to remove all suspended solid, otherwise actually it's going to clog this filter media, okay, or trickling filter media. So this is kind of, again, yes, it attached growth process, but you have to have primary treatment prior to this kind of process. Another process is called rotating biological contractor, or RBC. So where you have a actually rotating shaft, okay, which is kind of equipped with some media panel, okay, where actually biomass or microbes going to actually form biofilm, okay, and you are going to have a shallow tank, okay, of where actually wastewater going to flow through that tank, and when that that media panel going to be continuously rotating, okay. So you are going to have interaction. And why continuously rotating? This kind of system, it's not, you don't provide active aeration, okay. So you don't need to continuously supply oxygen because it's rotating, so it's kind of, there going to be some diffusion of oxygen in the wastewater, right, or inside the biofilm, and that's going to actually facilitate the process. And for this kind of system, the media panel is actually 35 to 40% submerged. So you don't it's not going to be completely submerged, it's going to be 30 to 40% submerged. And microbes, they are going to actually form biofilm in the filter media, okay, or not filter media, actually that media panel, rotating media panel. And this is like a biofilm process, okay. So biofilm process is little bit complex than suspended growth process, because biofilm process, so this is an aerobic treatment process, right. But still the inner film of biofilm in your media can be actually anaerobic. And why is that? There may not be, depending on how much dissolved oxygen level you have, there may not be enough diffusion in the inner layer of the biofilm. So what I am talking about here is So let's say you have a media, okay, and you have biofilm. So biofilm typically it's not monolayer, it's going to be multi-layer of biofilm, right? So you are going to see the inner layer, there could be some anaerobic bacteria, or actually outer layer going to be more aerobic. Because then why inner layer could be anaerobic? Because there may not be enough oxygen diffusion in the inner layer, right? So you know, like there could be you know, this kind of situation, okay, where inner layer could be more anaerobic instead of aerobic. And typically this kind of system you also have optional you know, like feature for providing air in the system, because sometimes there might be some situation that you know you don't have enough dissolved oxygen, right? So it's better to have some option. If needed, you can actually kind of aerate the tank for certain period of time, okay, and then you stop when you maintain or when you actually reach adequate DO level or dissolved oxygen concentration. So attached growth, and but this kind of like, you know, filtered system or trickling filter, I was talking about, like, you know, clogging might be an issue, right? But so to solve this kind of problem, another researcher, they found another design could be more convenient, which is called fluidized bed reactor. So what is fluidized bed reactor? So fluidized bed reactor, you have, like, you know, different types of inert media, okay, it could be plastic or other biomaterial or any natural material. So where actually microbes, they are going to form biofilm, okay, and instead of a packed bed of this kind of media, you can have, like, you know, less amount of those material, and wastewater going to flow at a, you know, like at a certain velocity that you can actually fluidize that. You are going to fluidize those media inside the reactor, but you have to make sure that velocity is not very high, that actually those things leave the system, right? So, and this kind of system can be either aerobic or anaerobic, okay, depending on what kind of process you use. So particle, they are going to be in suspension and they still can be retained, and they are going to provide large surface area, okay, and excellent you know, like interaction between microbes and contaminants, and easy particle handling, okay, and no issues with clogging because you don't have a packed bed. And there could be different types of media, like as I mentioned, there could be some plastic media, as you can see, with different geometry, okay, complex geometry. And why different geometry? Maybe, you know, researcher, they tried different shape and found that, okay, you know, some geometry could be better than others, okay, depend, you know, like for you know, biofilm formation, okay. But okay, from this figure I cannot really tell which one is better, but you have to do some research and see which one is actually give you better you know, biofilm formation. So in addition to plastic media, so those are morely commercial plastic media. You can see some commercial name, active cell, you know, like Aquafus. So those are commercial media. But you can also use some other inert media, like, you know, you can use lava rock. Those are more like natural biomaterials. There could be natural zeolite, okay. So those are before biofilm formation, and those photograph actually showing after biofilm is formed, okay. So you can see, if I compare with this one with this one, you can see, like, in the inside interior portion of this media, biofilm has been formed, okay. And another actually widely used, okay, design for you know, wastewater bioreactor is afflow anaerobic sludge blanket reactor, or UASB, okay. This is a very popular design for, especially for industrial wastewater treatment, okay. Afflow anaerobic sludge blanket reactor. This design actually has been developed in 1970s in Netherlands, okay. Initially it was designed for brewery wastewater treatment, but later on it's kind of became very popular in industrial sector, okay. So if you are working with like high strength you know, industrial wastewater, okay, and you want to actually recover methane as a biogas, okay, then this kind of design can be very popular. And the unique feature of this design is microbes, they are going to be still in suspension, but those microbes going to be in granular form, okay. They are going to form actually, you can see this is kind of like microscopic image, okay. So you can have so microbes, what is the size of microbes, any idea? They are in micrometer range, right? That's why you call them microbes. But you see those granules can be 1 to 3 millimeter in diameter, right? So and that actually granulation process was actually a part of this, that reactor development. So typically this kind of granulation, it's like more like self immobilization process of microbes, okay. This kind of granule is actually formed in SBR reactor, okay. So SBR reactor and over time microbes, they form like, they kind of one microbes, they attach to each other, okay, attach to each other and they form a large flock or granule. And sometimes this kind of process is accelerated by adding divalent or trivalent, cations. And why is that? Because like the surface charge of the microbes, they are microbes most of the time, they are actually usually negatively charged, right? So microbes, they are negatively charged. So when actually you add divalent or trivalent cations like calcium, magnesium, okay, iron, okay, so it's going to actually help them to actually form flock, okay, and over time they are going to actually form large granule. So then actually you can put them inside the reactor, okay. So in wastewater going to actually enter to the system from the bottom, okay, but and it's going to pass through the large, like the dense bed of sludge granule, where microbes, they are going to degrade, anaerobically degrade the organic compound and produce biogas, okay, produce biogas. So biogas is going to leave the system, effluent also going to leave the system, but at the top you have a like design, it's a deflector that's going to actually allow, that's going to make sure that granules, they are actually they are going to actually retain in the system, they are not going to leave the system, okay. So this is kind of like the unique design of the USB reactor. And initially it was developed for brewery wastewater, but over time it became very popular for other industrial wastewater like distilleries, fermentation industry, food, pulp and paper industry wastewater. Actually it became very popular over time. So here we are done with the topic number 1. Any questions so far? No? Okay, so we are going to now move to the second topic for today, which is microbial kinetics and their role in wastewater treatment. Okay. So when I'm going to talk about microbial kinetics, okay, so for when we are going to cover some equation, I will try to actually write them on the board. And why? Because when I'm going to move from one slide to another slide, you are not going to recall those equations. But sometimes you have to go back and use some equation from previous slide. So instead of going back and forth, it is better to actually kind of write them on the board. Okay. So I'll do that throughout my lecture. So microbial growth kinetics, it's very, so to understand the growth kinetics, it's very critical for design biological treatment process. Okay. And why it's like important? Because like we want to treat our wastewater at a higher rate. We want a fast process, right? So we can have a smaller system with low cost. So microbial growth kinetics, okay. So we can actually so we can have different types of kinetic equation, okay. So that we can actually get from microbial growth kinetics. And those equation we can actually get different types of kinetic coefficient, okay, that can actually kind of represent the growth kinetics of the microbes that you are using in your system, right? And that kinetic coefficient can be finally used to actually develop some design equation. So what I was telling in this morning, that we know some kinetic parameter, okay, and we have some process parameter. So if we combine them in some mathematical equation, that can be a design equation, right? that we can actually use to optimize our system. We can change different numbers and see how the process behaves, right? And that can allow us to optimize the process. So that's the main idea. So before jump into some equation, so let's talk about microbial growth kinetics. So microbial growth kinetics, okay, if we have a batch system where we have microbes and we have organics, okay. So organics or food for microbes. So let's say we have a small bioreactor where we have microbes. So microbes we kind of represent with X. So microbes could be biomass, and S is the substrate or food. So what is substrate or food? It could be either BOD or COD, okay. So organics. So this is food for microbes. So if you have a batch process, what's going to happen? Microbes, they are going to actually utilize those substrate, okay. They are going to create new cells, right, okay, and substrate concentration going to decrease over time, right. So if I have a graph, so substrate concentration, so changes in substrate concentration, which is ds by dt, okay, going to decrease, and biomass concentration going to increase, dx by dt going to increase. So if I actually put them in a graph, how it's going to look like? So substrate concentration over time in batch process, it's going to decrease. On the other hand, biomass concentration, initially there could be a lag phase, because microbes they need some time to actually adapt with the substrate, right? So before they can start utilizing them. So there could be a lag phase, and it could be depending on what kind of substrate that you are providing. It could be from hours, it could be minutes, okay, we don't know. So lag phase, after lag phase, you are going to see microbes, they are going to exponentially grow, okay, because they started utilizing the substrate, they are going to exponentially grow, and after a certain period of time they are going to reach a plateau. So they are going to reach a stationary phase where actually their growth and decay going to be kind of constant, and you are going to see a kind of plateau there. But after a certain period of time, the substrate going to be limited, okay, because it's a batch process and they utilized most of them. So now at some point they won't have enough food, and when they don't have enough food, what's going to happen? They are going to start to decay, right? So now finally you are going to see a actually decay phase or death phase going to start, right? So that's kind of like a typical microbial growth curve in batch process. But in wastewater treatment plant, in cities, like we are continuously 24/7, we are using water, we are generating wastewater, right? So we need continuous process. So that means for continuous process, we need a balance between microbes and substrate, okay? So we need to actually operate the system in a way that we have a balance of both, okay? So now let's actually learn about more different kinetic parameter that we need to know for microbes. So first kinetic parameter is specific growth rate, okay? So specific growth rate of microbes, so rate of increase in biomass concentration, which is dx by dt, okay, is proportional to the biomass concentration of the system. So basically what we are saying, dx by dt, it's going to be proportional to the substrate concentration, and for each equation, okay, we are going to get a proportionality constant, right, or a kinetic coefficient. So here kinetic coefficient going to be dx by dt equal to mu max. Mu is the specific growth rate. Specific growth rate, okay. So we use it like Rg. So rate of growth, okay. So Rg is rate of growth, and dx by dt, so changes in microbial concentration equal to mu max. So this is the kinetic coefficient.
dx by dt is growth rate, right?
Yeah, growth rate.
But here it's rate of increase in biomass.
Yeah, so biomass increase means it's growing, right?
I was confused
Yeah.
with the
Okay. Yeah. So specific growth rate. So the second one is yield, kinetic parameter. So what is yield? Because microbes, they are going to actually utilize the organic, and they are going to produce new cells, right? So the rate of biomass growth increases with a corresponding decrease in rate of substrate utilization, okay, which can be expressed as this. So basically what we are saying, that dx by dt is going to be proportional to changes in substrate concentration, because microbes, they are going to use substrate, so substrate concentration is going to decrease, and dx by dt, it's kind of like going to be positive, right, because microbes going to grow. So here what we are saying, that dx by dt, it's going to be another term called yield, ds by dt. Okay. So here this is growth rate Rg, ds by dt, which is substrate utilization rate, RSU, substrate utilization rate. Okay. So what I do, I'll clean the board a little bit, and as I mentioned, I want to summarize the reaction in one side, equation in one side, so we can actually use them later on. So Rg dx by dt to mu max. Okay. You don't need to write, because lecture going to be provided, and I think you have the access to the lecture from yesterday, right? So okay, RSU. So now yield can be defined as a ratio of amount of new biomass produced, okay, to the substrate consumed. Okay. So so basically, if you look into the unit, gram of biomass produced per gram of substrate consumed. Okay. So yield is basically gram of biomass produced gram of substrate used. Okay. So now, so yeah, so basically mass of biomass formed, mass of substrate utilized. It could be, if I kind of write it for a biological treatment process, I can say mass of VSS formed, okay, divided by mass of BOD utilized in the process. So another example, so calculate the biomass yield for this.
Biomass, you are directly correlating with the VSS.
So yeah, so it's kind of volatile organics, right? So biomass is, we kind of consider it's volatile, but again, biomass, that VSS may have two portion, biodegradable, non-biodegradable, right? Like as we learned yesterday. So here you can see microbes, they are using an organic compound and producing new cells, C5H7O2N, right? You remember from yesterday? So the molecular weight of this compound is about like, so this is protein, 184 gram per mole, and molecular weight of microbes is 113 gram per mole. So yield gonna be, simple thing, yield gonna be 113 divided by 184, right? So about 0.61 grams. So yield for this process gonna be 0.61 gram of cells per gram of substrate used, right? All right. So and yield for aerobic process, you can see. So higher yield means, what is higher yield means? Higher yield means it's producing more biomass, right? So if we compare anaerobic process with aerobic process, you can see aerobic process yield is 0.4 to 0.8 kilogram of VSS per kilogram of BOD5. But yes.
Why we are focusing so much on quickly or
No,
utilize more?
VSS, why we are focusing on utilize? We have to maintain a certain biomass concentration in the system because microbes, they are the key, right? So I have to know how much biomass I have in the system. So from design perspective, what I should care, okay? I should care about, like, if I am an operator, okay, what I have to do? I have to meet the regulatory guideline, right? So if a government is saying, okay, you know what, you have to achieve less than 25 milligram per liter, I have to maintain 25 milligram per liter. So I need to know effluent concentration, and at the same time I have to know, to achieve that effluent concentration, how much biomass I need, right? So that's why we are talking about VSS again and again, yield again and again.
My question is different.
Yes.
I am saying, suppose we have ESS, TDS. Why we are mostly focusing on VSS here or microbial fluids? Is that it is quickly absorbed by the microbe, the VSS part? Because there are different kind of solids.
Here VSS is indicating microbes itself, right?
So it means VSS is quickly absorbed by the microbes. VSS.
So what I am saying, VSS is the microbes,
But what I am assuming.
but you are saying VSS is absorbed by the microbes.
Yes, because VSS is coming from the substrate.
No. VSS, yes, a portion of VSS can coming from the substrate, okay, but here yield, when we talk about yield, here VSS is actually microbes
So
itself.
your point is microbe is eating substrate and it is converted into
So
VSS.
okay, so in wastewater engineering, yes, there might be some VSS coming from wastewater, but we consider that as organics. It's a part of my BOD, okay. So I don't consider that as my microbes. Here VSS, I consider this is my biomass, this is my
That
microbes.
substrate is eaten by the microbes and
So that VSS can be kind of consumed by microbes, but after hydrolysis, okay. All right, so that's answered your question. I know it's confusing because we kind of use we kind of move around with
now what I am assuming is you are saying microbe is VSS, means substrate is eaten by the microbes and that substrate is converted into the VSS inside the body.
So you can any like VSS can be actually those COD and VSS can be, or BOD or VSS can be actually used. They can be interchanged, right? So because if you remember the very last slide or one slide before the last slide, I was talking about VSS actually represent particulate COD, right? So when, yes, you are right that VSS can also come from the wastewater, but that VSS is actually a part of my BOD or part of my substrate, but these VSS here is actually my microbes. I don't consider, yes, like microbes can degrade, okay, and then they can release the intracellular product, right? That can be used by other microbes, okay. Like from the decay product from one microbe can be used by other microbes. But from design perspective, okay, I am going to consider here yield. When I use like the term yield and use VSS there, that is my biomass or microbes, okay. So anaerobic process, you can see yield is 0.08 to 0.2 kilogram VSS per kilogram BOD. So it's low sludge production. So aerobic process always gonna give you high sludge production. Aerobic process gonna give you less sludge production. Yes.
Sir, suppose I want to treat some wastewater from dry industry.
Mm-hmm.
Then how will the Y or E will look like, and how to calculate the gram or the substrate? How should I calculate?
Sorry, can you please repeat your question? I could not please.
Clear water from dry treated industry.
Clear water from?
Dry treated, I mean the water having dye.
Mm-hmm.
So I wanted transparent clear water. So that in this case, how will I calculate the yield?
He is talking about the dyeing industry.
Yeah.
Wastewater. So he is saying he want to clear the water after treatment.
Yeah.
So he is saying
So, okay, the question is, so that so that dye is organic. So then how you are going to actually remove them using microbes?
Then probably you need to use chemical treatment.
Yeah.
Because if your dye is not organic in nature, bacteria is not going to use.
Mm-hmm.
So point is that everywhere you cannot apply the biological treatment.
Yeah.
So in dyeing industry, if you decrease the pH, you go around 2 or 3, even the color will be gone. That depends on what kind of dye you are using.
Yeah.
Otherwise, you use photocatalysis process in the laboratory scale or any other process. Yeah, or adsorbent. It will adsorb the dye, water will be clear.
So basically microbial don't work.
Yes, there it will not.
Yeah, if it's inorganic, then it's not going to be removed. Yeah.
Your dye is synthetic in nature, not organic in nature.
Okay.
Then the glucose oxidase can be used.
Sorry.
Color removal.
Yeah.
Glucose oxidase can be used. There is some mechanism.
Okay. Okay. Yeah. So, so now the question is, sludge management is a problem for industry. Okay. So why not we use anaerobic treatment for wastewater? Okay. So anaerobic treatment.
Can I answer?
Yeah.
Actually, one of the major problem of this UASB is immediate oxygen demand. Like the water treated by the UASB, it appears that it is meeting all the regulatory requirements. But once you drop that water into the nearby water bodies, so there they will eat up the oxygen immediately. That is called immediate oxygen demand. So that is one reason. And another reason, every industry is not having that much high BOD.
Yeah.
It is only suitable for food industries or pharmaceuticals where the BOD is,
BOD is really high.
12,000,
Yeah.
12,000, 14,000 or food industry.
Yeah. So anaerobic process works actually better for high strength wastewater. So when actually like COD or BOD concentration, let's say few thousand milligram per liter, then you can use anaerobic. But aerobic, they are more efficient when you have diluted wastewater, like really small concentration. Okay, and we are going to actually do some calculation on that as well in one of the following slide. So anaerobic process is not suitable for diluted wastewater. So now we talked about microbial growth, right? Substrate utilization, we talked about yield, but we know that when actually substrate concentration is low, microbes also going to have their decay, right? So we also need to incorporate a decay coefficient when we actually develop a kinetic equation. So another kinetic parameter, which is endogenous decay constant, Kd. So D for decay, K is for rate. So when substrate concentration is at its minimum, microbes gonna metabolize their own protoplasm, okay, and concentration of biomass gonna decrease due to the death of some of the biomass cells. So what we are saying that there are gonna be some decay, and that's also gonna be depending on, so rate of decay is gonna be depending on the biomass concentration, but that proportionality constant we are going to call it Kd, and we are going to put a minus because it's decay, it's going to decrease, right? Yeah. So now we learned about, like, we have growth, we have yield, we have decay, right? Three things. So now now we want to actually look into like kinetic part. Okay, so kinetic part, and one of the most common model, okay, that is used for biological treatment process, it's called Monod kinetics. So what is Monod kinetics? This is a kinetic equation that actually show the relationship between substrate and microbial growth, because we kind of believe that actually substrate is the limiting factor, right? When substrate is high, growth is high. When substrate is low, growth is low, right? So one biologist he is a French biologist, J. Monod, he actually proposed an equation, but that equation mainly came from So he actually proposed this equation for microbial kinetics. So basically, specific growth rate, and you have substrate concentration, and he actually introduced another term mu max, so which is maximum specific growth rate, and another term Ks, which is substrate half saturation concentration. We are going to learn more, but that equation mainly came from Michaelis-Menten equation. Okay, I think possibly you learned about this equation in your high school, right? For this is a very popular equation for enzymatic kinetics. So we consider that rate of of reaction gonna depend on the concentration of substrate, right? For a certain concentration of enzyme. So here, Monod, he actually assumed that actually microbial growth kinetics also gonna follow similar pattern. Okay, so what's gonna happen? So if we increase the substrate concentration or BOD concentration, microbe gonna grow, but after above a certain concentration of substrate, that growth actually gonna reach a saturation point. Okay, and we call this as mu max, maximum specific growth rate. And then he introduced actually another term which is called substrate half saturation concentration. So basically, at what concentration growth rate gonna be half of the maximum growth rate.
This is all for batch process, right?
This is for
Closed system, because we are not adding microbe from the outside.
yeah, you can actually apply that in steady state of a even for a continuous process, but at steady state. Okay. So Ks is a kinetic parameter that correlates substrate concentration with microbial growth rate. Okay. So what Monod equation is suggesting us, which is bacterial growth rate increases as a function of substrate concentration or BOD concentration, and gonna reach a saturation after to a certain level, okay, and become constant. So after that, even if you increase the substrate concentration, so here you can see it kind of reached a plateau, right? After that, even if you increase the BOD, it's not gonna growth rate not gonna increase anymore. Okay. So application of Monod equation, it used to describe microbial growth kinetics, and kind of this equation actually works for like most of the biological wastewater treatment system. So most of the biological treatment system, the fundamental step is actually it start with Monod equation. Okay. So even any complex system like microbial electrochemical technology, actually a topic that I'm gonna cover on day 4. So even for that system, actually during my PhD I used Monod equation to actually kind of mathematically represent this system. Okay. Yes, there was some electrochemical part, but Monod equation kind of like was the fundamental starting point there. Okay. So Monod equation can be used to determine the substrate concentration or BOD removal efficiency for a wastewater treatment process. Okay. So and another key thing I want to actually emphasize here. So microbes, they have for a certain type of microbes, they are going to be a specific Ks value. Okay. So microbes that can actually grow at lower substrate concentration, they are much more kinetically efficient. Okay. So aerobic microorganism or aerobic bacteria, they can grow at a faster rate at low concentration compared to anaerobic microbes. So anaerobic microbes, they need very high concentration for growing, right? Yeah, but aerobic microbes, they can even grow at low substrate concentration. So that means their Ks value gonna be lower compared to anaerobic microorganisms. So they are kinetically more efficient to remove organics. So one example, actually when I show this example, I think it's going to be, you can easily understand. So a consulting company is designing a biological treatment process using 2 different microorganisms in sequence. Okay. First one to rapidly reduce the pollutant concentration before they can spread, and second one to reduce the pollutant concentration to a target concentration of 1 milligram per liter. So we have two types of microbes, A and B. So mu max for A is 1 per day and Ks value is 0.1, and microorganism B has mu max of 5 per day and Ks value of 5 milligram per liter, and initial concentration of pollutant is 100 milligram per liter. So now what I am saying here, you have A and B and you want actually design a two-step process. Okay, so you are going to have two bioreactor, reactor 1, reactor 2. So first one gonna quickly remove the concentration, okay, or quickly remove the contaminant. Second one, you want actually reduce it to 1 milligram per liter. So now the question is, which microbes we can put here and which one we should put here in second stage. So we can actually evaluate that using Monod equation. So, and actually, you know what, like let me write it down. So Monod equation is mu max S Ks plus S. Okay, so this is the Monod equation that we are going to use. So first we started with 100 milligram per liter, right? So if you read the question, you have initial concentration of 100 milligram per liter. So first one here, it's going to be 100 milligram per liter starting point, and here we want to achieve 1 milligram per liter. So now I have the equation, this one Monod equation. I can put, so S is 100 milligram per liter, Ks we have 0.1 and 5. So you can see here for A at 100 degrees Celsius it's 1 per day and B 4.76 per day. So that means at high concentration growth rate for B is going to be higher, right? So B is going to be more efficient for at 100 milligram per liter. So I am going to put microbe B here. In second step, we want to actually reduce it to 1 milligram per liter, right? So now my substrate concentration, I am targeting 1 milligram per liter here. So if I, kind of plug those number, so what I can see, A is 0.9 per day, B is 0.8 per day. So A is slightly better than B, right? So we can still put A. So A is going to be more efficient for step 2 and B is going to be more efficient for step 1. Okay, I have some more example on that. An environmental engineering consulting firm is designing a biological treatment process for a food processing industry. The concentration of the target organic pollutant in wastewater is 2500 milligram per liter BOD per liter, and the company did some preliminary lab experiment with 3 different types of microorganisms. So now instead of A and B, we have A, B and C, and they have different Ks values. Okay, so based on kinetic information, which microbes would be more efficient for target pollutant removal to 15 milligram per liter BOD, sorry 25 milligram per liter BOD. So even without doing the calculation I can, so can you tell which one would be better? Why? Sorry, what? It has low half saturation, and if you even actually do the calculation, you are going to find the same thing, right? So 0.5, 0.2 and 0.14. So 0.5 is highest growth rate, right? So that means A going to be more efficient. So now we want actually now we talked about biomass growth, right? So we have couple of equation, and now you can see here for that mu I already have an equation, Monod equation, right? So I can actually replace that. So Monod equation. So now for growth I have another equation, so which is mu max X S Ks plus S, right? So we can have this equation. So yield, again the same thing. I have yield, yeah, this equation, right? So I can have substrate utilization rate. I can actually get an equation. So here, so substrate utilization rate RSU gonna be minus RG divided by Y, right? So that means minus mu max KX, X S KS plus S multiplied by Y, right? So, and there another term could be used, okay? So mu max divided by Y, it's kind of can be, we can replace that with A, which is maximum specific substrate utilization rate. So mu max minus Y, we can actually put K X S K S S. So K is mu max divided by Y, okay? So another kinetic coefficient. So why I am summarizing this, ultimately we have to use those kinetic coefficient, right? So now for growth, so we talked about growth, but we know that microbes, they are going to grow, okay? They are going to have decay, right? So they are going to be a net growth in the system, okay? So how we can calculate net growth? So net growth going to be, we are going to have growth and we are going to have decay, right? So Rg plus Rd, and we already have equation mu max, and we have equation minus k dx, right? So we can replace those, this equation with this and this equation, right? We can replace this. So now, so net growth gonna be, I think the board gonna be full. So dx by dt net gonna be mu max minus kd x. So basically we kind of like, we have this equation and then we have this one Rg and Rd. So again, we love to replace everything like mu with Monod equation all the time, right? So we can actually replace this part with Monod equation, right? So dx by dt, we are gonna get again mu max x s k s plus s minus k d x, right? Another equation. So now, yeah, so now we have a lot of equation there, kinetic equation. So kinetic coefficient for aerobic microbes, conventional activated sludge process, those are typical range, okay, that you are going to see. And so why you need them? Okay. So we can actually, you know, like those kinetic coefficient can be used to actually, if we want to do some design calculation or even modeling purpose, we need those kinetic coefficient, okay. So they are kind of like experimentally measured, okay. Researcher, they did some kinetic experiment to actually estimate this kind of parameter. So before we take a break, I have 2 more slides and then we will take a break, okay, before we jumping into design equation and a process parameter. So if we compare now we learned about like a little bit more on growth kinetics, right? And so now if I compare aerobic and anaerobic process side by side, okay, aerobic process high sludge production rate, anaerobic process less sludge production rate, require aeration, which is kind of like a significant operating cost, okay. Anaerobic process, we don't need any aeration. So aerobic process, we don't recover any energy because organics, they are converted to carbon dioxide and water, right? But anaerobic process, we produce biogas, which can be actually renewable, can be utilized as renewable energy. Yield, is higher in aerobic process.
More sludge.
Yeah, more sludge. Anaerobic process we have less sludge. But now Ks value for aerobic process is 12 to 60 milligram per liter BOD. But if you look into Ks value for anaerobic, 180 to 450 milligram per liter. Okay? And mu max for aerobic is 1 to 10 per day. Mu max for anaerobic is 0.1 to 0.24 per day. So only this Ks and mu max is kind of like the deal breaker here. Okay? That's the only thing, you know, why we cannot use anaerobic process everywhere. Okay? So that mu max and Ks is low. So, and we can actually also, you know, we have Monod equation now, so we can actually plug those number there and see whether what we are saying is correct or not. So BOD concentration in a domestic wastewater is 300 milligram per liter, and we target 25 milligram per liter BOD in the effluent. Okay, and for aerobic microbe, we consider mu max 1 per day and Ks 50 milligram per liter. So you can see here mu max 1. So we consider the lowest specific growth rate, and we consider almost the highest Ks value. And for anaerobic microbes B, we considered 0.24 per day and Ks 180. So we considered lowest Ks value. So most unfavorable situation for aerobic and most favorable situation for anaerobic. And now we are comparing. Okay. So now if we put those number in the Monod equation here, what we get for aerobic process 0.86 and anaerobic process is 0.15. So that means actually aerobic microbes should be more efficient for rapid removal, or you know, if you wanna achieve 25 milligram per liter BOD, then aerobic process is gonna be the option, and that's why aerobic process had been used more than 100 years still. Okay, so and at low concentration, like you know, if we put 50 or 25 milligram per liter, it's gonna be the same. So the take home message from the kinetic is we need microbes with low Ks and higher mu max, right? So to have efficient treatment process. So let's stop here before we and take a break, and then we'll continue with our topic 3. Okay, thank you. So let's take 10 minutes break. Okay.